everyone. We are the team of innovation, that is, the horse coders, from the world of Gati Shakti Vishwavidyalaya. Today, we are here to present our team's first mission, which is to share the knowledge on a basic version of autonomous robot, that is, the maze solver. Wait. What is a maze? A question is circulating in your wonderful CPUs, right? Just chill. It's basically a puzzle which we might have seen when we were small kids, or we might have created them by drawing some random straight lines on our books where we enter from one point and come out from other. So we are gonna solve such puzzles by using our intelligent maze solving robot, which is made by integrating hardware and software. We gave knowledge to our robot using a special language, that is C language. What is C language now? This is a basic language used by humans to communicate with their intelligent computers. It feels interesting, right? Let's dive into it. A bot has a smart brain like you, that is Raspberry Pi Pico. As has strong legs, it has powerful motors, which helps the bot to move. And it has a system which controls speed and direction of the motors, which is simply called a motor driver. It even has mouth and ears like you, which helps to sense its surroundings. That's ultrasonic sensing.
Now we are talking about the robot movements. We add the 4 basic movements to our robot. It's just like its dancing step. Move forward, turn left, turn right, and turning around. First, move forward. Both motor rotate forward about for time for 750 milliseconds. This makes the robot move exactly one block in the maze. After moving, the robot updates its location. Example, if it was at 8,5 facing north, after moving forward, it becomes 8,6. Second one, turn left. The turn left motor move forward. The turn left motor move backward, and the right motor move forward. This makes the robot rotate 90 degrees to the left direction. The robot also updates its direction. If it was facing north, and now it is known it is facing west. Third one, turn right. This is just opposite of the turn left. The robot rotates 90 degrees clockwise, and its direction update like this: north go to the east, east go to the south, south go to the west, and so on. The last one, turn around. When the robot needs to go back, it simply turn 2 times right. It's like 90 plus 90, and making a full 180 degree rotation is turn around. Now we talk about the sensor we have used. We have used an ultrasonic sensor. Now I am explaining how ultrasonic sensor work. Very interesting. When the robot wants to sense a wall, it sends tiny sound pulse using ultrasonic sensor to the wall. Then the sensor waits for the echo to return. The longer the echo takes, the farther away the wall is. The code measures that time and quickly convert into distance in centimeter. If no echo was coming or no echo was returned, the robot assumes that the path is clear. We set a 40 centimeters threshold. Like, if distance was greater than 40 centimeter, then the path is clear or no wall to this. If distance was lesser than 14 centimeter, there is a front wall in front of this.
I am here to represent a working video of a group project. Are you excited to experience a visual representation of a maze solving in action? Here comes an amazing maze solving robot with the ability to navigate complex mazes. Our robot begins its journey from the start point. When it encounters a junction, it marks the previous path as fun in its mapping system. It then analyzes the situation using its algorithm and checks inputs from all the 3 sensors. As the right side contains a wall, it marks it as 3. So the robot has only 2 options with it, to move forward or to move left. According to the biases we have set, our robot will move forward and continue the motion. The robot encounters a wall directly in the front, so the process repeats. The front is marked as 3 and the right side is also marked as 3. The only option remaining is to turn 90 degrees to the left and continue the motion. Here comes a dead end. The robot marks all the three sides as 3, executes a 180-degree turn, and traces back along its previous path. When the same junction is reached again, the robot reassesses the situation. The left side is marked as 3 as a wall is detected. The front is already marked as 1 as it is previously explored. The right side shows 0 as an unexplored territory. According to our algorithm, which follows the lowest number path, the robot turns 90 degrees to the right. The same process repeats. As a genius robot checks condition at each junction, making intelligent decisions based on its mapping system, continuing its motion through the challenging maze, it successfully navigates every twist and turns until finally emerging a victorious exit.
Now I will be explaining how the robot makes a decision. This is the very clever part. How does the robot decide where to go? We gave it a strategy. Step 1. Look around. The robot uses all three sensors to check left, front and right. It's asking itself which ways are open, which ways are blocked. Step 2. Check the map. For each open direction, the robot looks at its memory map. Has it been there before? How many times? It's like the robot is thinking, I have already visited the front square twice, but I have never been to the left. Step 3. Make a choice. Here's the priority system we program. First choice. Go to the square you have never visited before. Exploring new territory is always best. Second choice. If all nearby squares have been visited, go to the one you have visited the least. This helps the robot avoid getting stuck in loops. Last resort, if somehow you are completely boxed in, turn around and backtrack. Now I will be explaining how the robot stores the maze and its position. Our robot has a memory system. It uses an integer double-dimensional array of size 16 x 16 to store the maze. Imagine a piece of graph paper with 16 rows and 16 columns. That's our maze map stored in robot's memory. Every time the robot visits a square, it marks it down. If it finds a wall, it marks that too. This way, the robot builds its own map as it explores. The robot uses a structure named robot to store its current position. It keeps track of three important things about itself: where it is on x-axis, where it is on the y-axis, and which direction it's facing: north, east, south or west.